Hello and welcome to today's Happy Maths Hour. Thank you very much for joining us. And today it's about puzzles, games and proofs without words.
Can't
Toni,
guarantee that.
welcome.
There might be a few words.
But they're proofs that you can do without words.
Exactly. And as usual, it'll be just a chat. Caroline and I chatting, hoping to entertain you. So tune in to Happy Maths Hour. If you're with us, we're delighted to have you. And you'll see two pictures of Caroline and me there, and you've probably seen them before, but Caroline's doing some maths with bubbles, and I'm doing some maths with a little boy in South Africa, and there's in a classroom with other children around. Okay, so you also see two pictures there, and a lot of this is about squares, okay? So our first slide is about just taking a piece of paper that's square. Okay, pull it away from the screen and therefore you can see it. And folding this piece of paper and learning just from that action, folding it into four. And you can see it on the screen there. By folding it into a diagonal, as you see on picture number 1, and then you can see there picture number 2, folding it over and flattening it as in picture number 3, folding it again as in picture number 3, and then you've got here, you see, you've got 4 pieces in this fold.
I've got mine here, Toni.
Caroline's also showing you one. Okay. And then on the bottom you'll see, so now you imagine it, just keep in mind that the original triangle has been folded into 4, and the pencil at the top is showing you an angle, and number 5, and that's at the center where you have 360 degrees or whatever. You don't even need to know about degrees. That angle all the way around is divided into 4. So those are what we call right angles, or if you like, 90 degrees. Now, Caroline's doing it. So it's better than me holding it up. She's actually doing it. And you talk about it, Caroline. You say a bit more about what you're doing.
It's a really simple but very revealing investigation, because one of the biggest mysteries is, well, one of the things that people have to learn is about triangles. And for example, that a straight line is 180 degrees. Well, given that, that's a very, very powerful piece of knowledge when you're doing geometric proofs or working out angles with geometry, because you know that a straight line is 180 degrees. If you fold that line in half, then you know that each of those angles is 90 degrees. And with that knowledge, armed with that knowledge, and this one we've folded in 4, we know we've got 4 90-degree angles. Well, that would actually then be showing that each of those 180 plus 180 is 360 all the way around. And what we're doing with this is working out. I'm sorry, I forgot what we're doing. It's now, Toni.
I think
it's a square investigation, and it is based around the fact that we have 360 degrees. When we
a little more than. Can I just say something, Caroline? I mean,
yes,
basically, we were chatting about pedagogy last week, and this is what we're doing. And there's this emphasis in school for children learning properties of two-dimensional shapes. And the square is just a two-dimensional shape, okay? So what can they find out about a square? By doing the folding that Caroline showed you, not only do they learn something about angles, discover something, they discover something about the 4 edges of the square being the same length. Okay?
So we folded that one on itself, therefore that angle, that length is the same as the one below. And that length is the same as the one below that. But then when we fold them again, we discover that for sure, we're certain that all 4 lengths are the same.
And then another thing that they can see is when you open it all out again, that the diagonals of the square bisect each other, and they divide the square into 4 right-angled triangles. And so there's a lot of interesting things about the square. And then you can turn it round and you can see it's what we call, it's got rotational symmetry. So there's many things about the square that you can discover just by folding a piece of paper and not tell the children these properties, as Caroline and I are telling you today, but ask questions. What do you notice about number 2 and number 3? But actually, with the children having paper in their hands and doing the folding, what can you talk to your friend? And, then we're going to ask you can tell us what you found out about this shape. So it's a way of teaching which is organized around the teacher asking questions rather than telling children facts, and the children finding out for themselves, guided by the teacher, and being given activities, in this case folding a piece of paper, from which they're going to notice some mathematical properties which they won't necessarily know the name of. They won't. I mean, I was talking about rotational symmetry of this shape. Well,
when I say it, I just say it looks the same whether you have it that way or that way or that way. It looks the same, but this is for younger learners, but it is actually facing a different way. So that is rotational symmetry. But all you need to do is say it looks the same, because that's the whole point. It must look the same if it's got symmetry.
And then you look at flowers and you look at other objects, and you see that you can turn them around so they look the same when they're not turned all the way around, but when they're only turned part of the way around, they look the same. And you can see rotational symmetry, but not for 4 turns, but maybe for 5. A flower with 5 petals on, a sort of daisy-like flower with 5 petals on, has rotational symmetry of order 5. So you're looking at...
One thing I like about this as well is that one of the questions that gets asked a lot is that how do I know that this is 90 degrees on a square? Well, I've taken an A4 sheet of paper, a normal piece of paper, and that has right angles on it. But if I hadn't started with a piece of paper with right angles on it, how would we know that this here is a right angle, which comes, we need to know that in a minute. We're going to really need to know it as one of the activities we're going to do. And it's by, when you fold it through the middle, you know that those are right angles because you've folded them on themselves, and it makes a total of 360. They're divided exactly into 4, so you know each one is 90 degrees. And then you know that these edges are exactly the same length, therefore these angles are the same, and that's 90 degrees. So you know that another investigation lets you know that 180 degrees, which way up are we doing this? If I write that, can you see it? You can't see it. But anyway, all 3 angles add to 180. Therefore, that plus that makes 180. Therefore, that and that is 45. Therefore, that is 90. And it's actually a progression, and you can actually prove to I don't, is that an actual proof, Toni, or is that simply to my satisfaction?
Well,
or is that an actual proof?
Well, you can turn it into an absolutely rigorous proof by stating it very precisely, but it is, yes. And I mean, to repeat it, if you look at diagram number 6, would you like to put the slide back and we'll carry on?
Yeah.
But if you look at diagram number 6 there, you can see the pencil, that's the square folded into 4 equal triangles, and number 6, the pencil is on an angle there, and you could fold it again and you could see that the angle on the other side of the base is the same, and your angles add up to 180, and that the angle there where the pencil is in number 6 must be 45, and there are 2 of them at the corner there, so they add up to 90. Yes, we do another lovely paper folding thing which proves the angles of a triangle add up to 180. That's called Trifold.
And that's another proof without words. I mean, you do use words, but you can see it. It's tangible. You can hold it in your hand and see. It's just obvious. And
Caroline,
it's
I think
beautiful.
it's about time to play a game, don't you?
Oh, yes, yes, yes. I love playing games. Are we ready? Go ahead.
She's crazy about games. But before we play the game, Caroline's a bit excitable today, because we're celebrating Caroline's birthday today. So happy birthday, Caroline! What does your badge say, Caroline?
It says
60.
birthday girl. No.
Oh,
It says birthday
have I
girl.
given away a secret?
My great nieces and nephews, they were going off in the car, and the mother had to stop the car and come back because the children they'd forgotten to give me this, so I have to wear this all day long today.
Her birthday girl. Okay, so let's play a game for the birthday girl. Okay, so let me explain the game, and then we'll play the game against each other, but we'll do it on a computer, which will be fun. And we'll give you the link so you can play it on the computer, against the computer, either with a friend, so you just do it as we'll show you, or you can play against the computer and see if you can beat the computer. But on this slide, it says, play for fun, think to win, play to learn. Okay. So you've got to make a square in your color. Now that's the object of the game. That's why it says that at the top. And you either choose to be blue or red to start with. Okay. And once you've chosen your color, you're going to put markers on that board of your color, little counters or something. Now, go back to play for fun. Of course, people like games, but they usually want to win. And to win, you've often got to think. You'll find this is one of those games, and you've got to think mathematically, critically, logically, in order to win. And so it's really good for developing your critical thinking. And while you're playing, you're learning. Okay, you're learning all sorts of strategies and mathematical ideas.
And
So,
the thing is, it's we'll see we have diagonal squares, and this is a huge issue with learners of all ages, even adults. They're like, yes, but if it's tilted, it's not a square, right? Because they're thinking it's a rhombus.
you've taken away the element of surprise.
The point, I'm sorry, I'm spoiling the surprise, but it does. The point is, it deals with some of these deep-seated
So how do you tell somebody, if you're doing it online, for example? Well, you can click on it, but if you've not got like a computer game where you can click, how do you tell somebody where, if I'm blue and I want to put it where you see it on that, I want to put it on that particular spot, then I give the two, I say it's on D4. Okay, so it's D across and 4 up, and that's where the blue marker is. And the red marker is on E, which is across to E and then up 3. So that's E3. So the game runs like this. It's the first player to make a square in their color is the winner. And you take it in turns to claim one of the dots with your marker by putting your color on that dot. Okay. So Caroline, this...
Ready?
Yes, this is the link for it, which we will give you to the Enrich computer. Caroline is going to put that up, and we're going to play this game against the computer.
Are you ready now?
Yes, yes.
Okay.
Right. There it is.
So you can play it as one player. In other words, play it against the computer.
Can you make it larger by going full screen, Caroline, or is this as large as it'll get?
This is as large as they can get within StreamYard.
Okay, that's perfect then. Okay, so we're going to make it a 2-player game, shall we, Caroline? And I'll play against you.
Yes, let's play a 2-player game. Now,
and we're just doing it as a demonstration and to show you, and then you can, if you're interested, you can try it for yourself.
Okay, so using Toni's nomenclature, you can go first, Toni. You're the senior.
Okay, so I'm going to go on C3.
C3, so that will be this one. I'm going to go on B4. C4.
Right, so I'm going to go on D2.
D2. I'm looking at this is using, I might be in trouble already. Okay, I'm going to go on E2.
Okay, so I am going to go on, let me just see now. Right, I'm going to go on D1.
D1. Okay, I think Tony's got best strategies than I have. Wait a minute, what am I doing here? Thinking, yes, I'm going to go on C1.
Right. Okay, I'm going to go on C2.
C2. Okay, now Tony's forcing me to go on D3, but if she might have already managed to get 3 and I haven't noticed them, not sure.
No, not yet.
Not
yet. Right.
But Tony's got the head that she's ahead of me because she's got some
well,
she's got a couple of places where you're forcing me to go in a particular place.
What shall I do? I'm going to go on well, I'm going to go on B2.
B2, right. So now I have to go on B3. And Tony spoilt my square that I was working on there.
So I'm going to go on B5.
B5. What's she doing? Oh, I'm looking for odd squares. I'm looking for what is Tony doing?
No, floundering is the answer, Caroline.
Okay, well in that case, it's not like you to flounder.
Okay. Yes. So, so I think I am going to go on.
Sorry, I didn't say I'm on C5. Go on.
D4.
D4. You haven't won? You haven't won yet, right?
I haven't won yet.
I have.
Oh, brilliant. Now, this is what Caroline was talking about earlier. Okay. This is a square. Can you see? It's a square. And what she has managed to do is beat me, of course. Brilliant, Caroline. Well done.
It doesn't happen very often, folks.
And I hope you can see that even though it's tilted, we call it a tilted square. And this is a surprise to many people. They'll say, oh, that's not a square. And what they're imagining is the square has to have the edges this way horizontal and this way vertical. But of course it doesn't. You can have a tilted square like that. And we'll talk more about that. So we'll just leave you with the thought that this is a great game. You can just make the dots on a piece of paper with a pencil and play it against a friend. And if you don't have colored markers, you can put a cross for you, and your partner can put a circle around it for them, around the pin for them, and you can play it with pencil and paper.
I'll show you on here. I play this on Zoom with my tutees. it's part of our thing. It's like, okay, we've had enough, now it's ready to play a game. But it's a very valuable game. So it helps with visualization, it helps with understanding squares, it helps with problem solving, it helps with lots of things, and it's fun. And yes, so we might do, we use the 1 to 5, 8, A to E, if we do a 5 by 5, and then one does a circle and one does a cross, and then sometimes one of us has won and we don't even notice because we don't have a computer to tell us that we've won. But it can be done between two people anywhere on Earth, as long as they've got the means to do pencil, paper, and the means to see, or they can both record it independently as well.
And the others, you see, there's so much you can learn from this. I mean, for example, the red lines that you see in the game that Caroline and I played, you can learn about gradient, and you can learn about the conditions for lines to be at right angles. So, for example, the red lines on the edge there have gradient, what we call gradient 1. And what that means is that for every time you go across one, to get the next point on that red edge, you go up 1. So it's gradient 1. And the other edges have got gradient -1 because you go across one in the other direction, which is the negative direction, to go up 1. And so you've got those two lines which have gradient 1 and -1 at right angles to each other. But of course you can have other gradients. It's just happens that that's the tilted square we've chosen today. So can we go back to the PowerPoint, Caroline? There it is. Now, there's something that's a lot of fun, which can be a party game, or it can be something that the children do in class, or you can mark out a grid with, in this case, it's only got 16 chairs and 16 or if you want to, you can mark it with points on the ground in which people can stand, so they don't actually have to sit on a chair. And so the way you play this is exactly the way we played the game against the computer. So, but you can have two teams of people, and so they tell the member of their team, the first team to go says, go and sit on, and specifies which chair the person's got to sit on. And then the other team sends somebody to sit on another chair. And just like Caroline and I use red and blue to claim the points on the board, you can use people, or they can have, colored shirts or headbands or cards they hold up that show which team they're on, or you can have boys against girls or something like that. And it's the first team to have 4 of the members of the team sitting at the corners of a square on those chairs, either a straight across and straight up square or a tilted square, but any square. It's the first team to get there. 4 team members sitting on 4 chairs in a square that wins the game. And of course, it doesn't have to be chairs. It can be just points marked, in those places. And the great advantage of people maths is that by physically engaging with activity and not just keeping still, but actually moving around and being part of the action in the mathematics, it makes it more memorable for children to remember properties. And of course, they're learning while they're playing the game. So that's people maths. So let's move on to the next one. These are called Geo Boards. Geo Boards, wooden boards, and you use rubber bands on them, or the one on the right, I've used some string to demonstrate something on that board. And on the top left, you have some ladies. You can see they're knocking nails into the board with hammers, and they're making their own geoboards. So the way we do it is they have a square with the points marked on it of paper, which they stick on the piece of wood, and then they know exactly where the nails should go and place them, knock them in precisely in this grid, and making they can make a 5x5 geoboard is the one in the middle. They can make a 3x3 geoboard as the one on the left, or they can make a circular geoboard, and that one has got 18 pins around a circle.
And there's a pin in the center of it as well.
And then you need
what's beautiful about that is you can literally play with all the different shapes you can make, and you've got the flexibility of a rubber band, which means you're not limited to squares. And
you need some rubber bands.
Oh, can't see those, Toni.
Oh, well, never mind. You can imagine them. You need some rubber bands.
Yeah.
And it's a interesting. One of the teachers who came on one of our courses said, "Oh, when I go back to school, it's the woodwork technology class that's going to make these, and I'm going to make all the learners in that class make one, and then they'll be used as a class set in the school, and the children will all be able to use these geo boards." And there's so much learning that they give rise to. They're a very nice little device for doing geometry and doing it quickly and easily, because it takes quite a long time to draw a square or a triangle accurately. But immediately, in just a fraction of the time, you can put your rubber band around the pins and make the different shapes.
And there are great apps you can use, and we're going to be sharing one with you in a minute. But the doing it with your hands on, it's a visceral learning. It's something that you can visualize so much more if you've actually had your hands and your eyes all immersed in it, rather than and you still have the flexibility of being able to make any shape that you can make with that pattern of nails.
You might like to make one at home with your children, and then you can look up geoboards on the web, and you can remember some of the things that Caroline and I have talked about, and it makes a great activity for the home, a toy that they can learn from playing with. Now, can you see this, Caroline?
Yes, we can see that. Come
let me bring it closer to the camera. Okay. Yeah. Now, can you see that it's got some rubber bands on it?
I'm just going to turn my light off so I can see, because I'm being dazzled by my light. Yes, we can see the rubber bands. Yes, we can.
Right. Now, that has got 18 pins around it. It's the same geoboard that you see on the slide, but I've marked out 3/18ths. Right, so this is to show you how you can use this to do fractions.
Right, so there's 18, the circle's made up of an 18 are gone. So it's got 18 pins and 18 edges if you were going to join them all.
Yes,
and you've taken 3 of those with a rubber band, and you've split that, even within the 3, you've split that into another 3. So you've gone with 3, and then you've got the rubber band coming down from each of those onto the center.
Yeah,
so you've got 3/18ths. So you've got 3/18ths.
And I'm going to show you another image about this in a minute, but you'll see how powerful it is to add fractions. And what you can see as well from this is that as I went round these pins, the 18 pins, I could do this 6 times to fill it all up. Instead of having 3/18ths, I could have 18/18ths, and each section is 1/6. And you can mark out different fractions and add them up.
And use different color rubber bands to indicate the different size fractions. Yeah, I said it wrong. It's not 3/18ths. It's 3/18ths making 3/18ths. So you've got 3/18ths marked out of your whole total circle.
And 6 of those will fill the whole all the way around, and so they're each 1/6, and that is showing you the fraction 3/18, or 3 divided by 18 is the same as the fraction 1/6.
It's equivalent to 1/6. Okay, and it's visual. It's lovely. Yeah.
But there's lots of ways you can use and play with these and learn through playing. So there's an app online which you can get on your phone, and there's the link to it.
There's a link to it, but you can just go to your App Store or your Google Store and just type in Geo Board, the last 8 characters, and just get it at the App Store.
Now you'll see they're black, and you can see the circular geoboard on the top right there with some writing around it, and you can see the rubber bands at the bottom, different coloured rubber bands. But there's only 12 pins around that one, and so it's marked out with 2 12s, okay, and it's marked out, the green is actually 2 12s, but the 2 12s make a sixth. And so you can see that the green fractions are 6, and 3 of them, if you look at that, is it 3?
Yeah,
2 6. 2 6 make a third. Okay.
And then if you put up the yellow and the green, you've got 3 6, which make half.
Yes. So
and you can also see from there is that a third plus a sixth is a half. You can see that from there.
Isn't that beautiful?
Visual. I'd never, yeah.
So you've got lots of ways of learning about adding fractions by using the circular geoboard. And the one that's divided into 12 is good, actually, because you're already used to the clock face divided into 12. So that has a lot, you do a lot with it. And the other demonstrations on there were done with the same app. I did them with the same app. And the two that have got quadrilaterals on them are showing you the different quadrilaterals that you can make with just 9 pins. So what I've done is divide the board there up with the red rubber band from top to bottom. It's got coloured rubber bands on top of it, but basically it's divided up so that each of the quarters of it is showing you a 3 by 3 array. And so you've got a square and a parallelogram in the top left area of 1, and you've got a quadrilateral with area 2 on the right in yellow, and in green you've got on the bottom you've got a rectangle area 2, and then you've got a trapezium. You can see it's got parallel edges in orange, which is area 1.5, and then going over to the right you've got another different parallelogram and another trapezium, and or 2 more trapezia and some more quadrilaterals. So you can see the question that we asked was how many different quadrilaterals, 4-sided shapes can you make? And there are lots of them. And then on the bottom, on the right, there's some we asked the same question about triangles. And so your children can play with it and find as many different triangles as they can on a 3 by 3 pin board. And you see lots of triangles. So this is something that you can play with just a piece of wood, okay? And it can be a 3 by 3 board, or it can be any number of pins that you've decided on, and it can be the circular one, or you can do it on the app. But I actually recommend the physical thing. So the question that you might ask is, how many squares can you make on 9 pins? Now, this is a slightly different question, and these are now different squares, just in different places, but anywhere on the 9 pins. So just think a minute. How many squares could you make? What areas would they be? Okay, so we're not going to dwell on this. This is not a maths lesson. This is more a chat. So here we have the 6 squares. Okay, and if we call the one in the middle at the 4 that are all the same, if we call that 1 square unit of area, then the one on the top left is 4 square units. And the one just underneath it is like the square that Caroline made when she won the Square It game. It's a tilted square, and that's area actually is 2 square units. And you can
it's fascinating to actually work out the unit, the area, when there are diagonals. And at first it can be a big mystery, but once you start to see it, and we're going to talk about that again in a minute, but once you start to see it, a big light bulb goes on, and you can get really excited about, well, I can, about actually finding the area of things, it makes so much sense suddenly. Go on, what have you got there, Toni?
Well, what I wanted to do is to show why that area, if it was the same size as this board here, it would be even more convincing. Why it's half. You see, I folded the 4 corners down into the center, right? And I'm
going to do that too. So I've got my square here. I'm going to fold the 4 corners of my. So this is area. What that would be 4 square units if we're looking at these. Yeah, I would have 4 squares on there. Now I'm folding it down into the center. So I've got literally I've halved the area. So I have the same amount of paper on the bottom as I have on the top.
And you turn a square that is the edges are horizontal and vertical into a square that is tilted when you do that folding in.
Okay, let's have a look at that for just keeping it still there. Just let the camera catch up. Oh, it's moved. It's decided to sink down. Okay, so we've got a horizontal and vertical square, and I'm going to fold in. I'm going to literally halve the area of it. That's by the by, in a way. I'm halving the area, and kapow, I have
a tilted square.
A tilted square. But I discovered something else as well, Toni. By doing that, I'm also proving that those 4 corners for 4 vertices are 90 degrees, because they come together and sit directly over that central one, and they add up to 360, and they're all the same. So because we proved that, because we folded them over on each other. So pretty, that also shows that they're 90 degrees. Each of those vertices is 90 degrees, which shows that this tilted square is a square because we folded over a square. And so this tilted square is definitely a square. These are definitely 90 degrees, because we've got exactly the same rule, that we've got the 90 degrees joining together in the middle. So these 4 vertices are 90 degrees. Therefore, this is a square. And we could, again, if we needed to, we could fold it over to prove that this edge is the same length as that edge, and that angle is the same edge, that those angles are the same as each other, if we need, if we feel the need to. And there you have, those edges are all 4 edges are the same.
Isn't it amazing what you can learn just by folding a piece of paper? And of course, it's a bit like origami, and origami is great for learning mathematics. But this is very simple. You're not, anybody can do it, even quite young children. And rather than telling them properties of a square, they can discover them for themselves. And so let's move on. Now, look at this side. We've just done 9 pins. What about 16 pins? Now, I'll give you for free that there are 20 possible squares. Can you find them all? So there's a challenge. And I'm not going to give you the answer to that. If you want to try it's a challenge. If you want to try and do it instead of playing Sudoku or a crossword or Wordly or something, or whatever, you can have a go. And then here's another puzzle for you. With 25 pins, there are 50 squares altogether. Can you find them all? Okay. And
you have to use the math skills. So this is again where, by playing these games, you're gaining math skills. So you have to do things like be systematic. These are the skills you need, A, to be an effective mathematician, and B, they very, very useful life skills. So in order to find them all and to know you found them all, you have to be systematic, you have to be well organized, and you also have to reason with yourself to make sure you have actually found them all, or you could reason with somebody else. These are all very important, A, mathematical skills, B, life skills.
Yes, and yes, and if you like puzzles, there's a challenge for you. And you could do it on your Geo Board or dotty paper. In fact, if you go to the link on the Aiming High website, there's grids of dotty paper that if you can print them, you can use. Now we're going to move on to another.
The link is in the description.
It will be, yes.
It is in the description, Toni.
Let's think about another jigsaw. And this is a very simple jigsaw. And it has only 7 pieces, okay? And 4 of the pieces are identical. If you put them on top of each other, they exactly match and correspond. They are the right angled triangles at the bottom there, the 4 blue triangles. And actually, those can be any right angled triangles. They don't have to be.
As long as they're all the same. Any right angled triangle that you want, as long as all 4 are exactly the same.
Yes, I mean, you could have the half a square. I mean, you could have those angles equal, but obviously that would be rather a special triangle. And these are just any triangle.
Yeah, the joy of this is that it's any random triangle without symmetry. That's the joy of it.
And then
right angle, critical, it has to be right angle triangle.
Yes. And then the squares are made in this puzzle so that the edges of the green square are exactly the same as the shortest edge on the blue triangles.
So the green square matches the shortest edge of the triangle, okay?
And the orange square matches the other edge that's not the longest, not the shortest. Yes, the one between.
The baby bear, the mother bear, and the father bear. So it's the mother bear length and the medium length.
It's the one that's straight across in the way you see it there.
The horizontal one, yeah.
Yes, yes. And they exactly match. And so you can make your own puzzle and following what Caroline and I are talking about.
And then the pink one follows the diagonal. Otherwise, if you remember this one, it's the hypotenuse. The pink one is exactly the same length as the diagonal longest edge.
The longest edge of the blue triangle, right? Now then, there are 2 puzzles. You've only got 7 pieces, okay? And you can select 5 of these pieces together to make a square, okay? And then all right, once you can do that, you can start again and say, now back to my 7 pieces, which 6 pieces should I put together to make a square? And for very young children, to make it easier for them, and we'll show you this in a minute, you can draw an outside frame of your square into which they've got to fit those 5 pieces. And then when they do it with the other version, they've got to fit the 6 pieces into this outer frame, which is a square frame. Okay, so to make it easy, you can give them a square frame, and then you can show them one way the pieces fit into the frame, and then you can jumble up the pieces and ask them. We're going to show you the solution in a minute. And then you can jumble up the pieces and ask them to put them back into the frame. And they've just seen it done. So they then will try to put them back. And if they've got a very good visual memory, they'll be able to remember what you showed them.
Yeah, it's a challenge. It's enough of a challenge to duplicate what you showed them. That's a nice challenge. And then once they've done that, then if they don't automatically find an extra possibility, but that's a nice challenge just in of itself.
And you might not
learners.
show them. You see, you might not show them all 7 pieces. You might know which 5 pieces to choose and give them those 5 pieces and say, can you put these into the this frame to fill the frame, to fit it all up so they fit tightly together and neatly together. And of course we've given you a clue, because we told you that the green will go neatly up to and exactly snugly fit against the short edge of the blue triangle, and the orange will neatly fit against the medium length edge, and the pink one against the longest edge. So you can make it easier for the young child by giving them the pieces and saying, put these 5 into the frame. And then,
can you just repeat that, Toni, because I had a terrible interruption? Can you just go back so that I can for the recording, please?
Okay, so what I'm going to say is, to make it easier for the young child, you can give them the 5 pieces and say, put these pieces into the frame. Because it's much more difficult if they've got to choose 5 from 7 and then try and do it. And of course, you can give that sort of challenge to the older person, or to an adult. But for the very young children, it's an easy puzzle, and they'll enjoy doing it. And what you're actually doing is you're laying the foundation for later learning, which will be really valuable foundation. And Caroline and I talk about the spiral learning path. We often talk about that. And what you're doing, if you do this with young children, as just a game, and once they get tired of it, then don't press it. Just ask, maybe come back to it another day, or they may will actually come back to it.
It's lovely when you're playing with really young learners. You might introduce the toy itself, so you introduce the pieces and let them completely do whatever they want with it, and then you might maybe make a different square with it, and they might notice, or you might say that you've made a different square, and then you keep bringing the game out and playing different things with it, and it does evolve. It does evolve into them then creating their own squares. Some are more interested in the squares sooner, some take longer to be interested in the squares, but it does evolve into a more from free play into something that's more inquiry and with an objective, but it still remains play, but it's slightly more guided. But it does happen. All you need to do is play it alongside them, and they'll be looking at you and looking at what they're doing and think, well, I want to do what in my case sometimes grandma or whoever, and they get curious about what you're doing, and then you can say, well, what could we do this other thing, and they get and it's interesting how even very, very young they can get very curious about it and investigate it, and then they'll go off and I've had enough now, go off, but you can bring it out again another day.
So what Caroline and I have been doing this afternoon is we've been building up to this point, because we've been introducing folding a square piece of paper, and what we can find out about the square from that. And then we looked at Geo Boards, and then we looked at how many squares can you make on this Geo Board, and the tilted squares. So we were actually laying bases for this particular interesting idea that we're in the middle of talking about. So now when we come to upper primary, which is sort of 8 to 11-year-olds, now the children can cut out the pieces from a template to make the puzzles, because of course you would do the cutting out, which you had 5 or 6 or 7-year-old probably, but by the time they're 7 or 8 or 9, they should be able to cut the pieces out. So you print the pieces maybe, or you can actually do more than that. You can actually draw them from scratch if you haven't got a printer. And when they found solutions, they should be able to draw diagrams of those solutions. And as a parent or teacher, you might encourage the children to find all the solutions, because there are several, not just one, and variations. And they can come back to it on other days. They don't have to find all the solutions on the first day. So there's a lot of scope. And you see, we've now developed from something a little more challenging for the slightly older children. And now we're not necessarily giving them the frame. I mean, they might, once they've got a solution, draw a frame round it so that they now know what the frame needs to look like. And for 11-year-olds and older, they can make their own puzzle pieces, following the description that we gave you earlier. That the blue triangles, as long as they're right-angled and as long as they're identical to each other, and you have 4 of them, and then you make the squares by matching the edge lengths to make sure they fit against the blue triangular pieces nice and neatly. So where do we go from there? Now, there are 2 solutions, okay? So imagine the frame. Look at it and think about those 2 solutions. So each of those, solution 1 and solution 2, the 5-piece solution and the 6-piece solution, they fit, they're 4 triangles. You have to look closely to see that those rectangles are actually made up of 2 triangles put together. And on the slide, it may be difficult for you to see, especially if you're looking at it on a phone. Okay, but now you should be able to imagine this, that what you have done on the solution 2 is you made those 2 blue rectangles, the 2 blue rectangles, by putting 2 triangles together to make the one that's across at the top, and 2 triangles together to make the one that's up and down on the left-hand side.
That's a huge revelation in of itself, is the amount of shapes you can make using 2 triangles, or just using triangles. That just to know that a rectangle is actually could be made out of 2 congruent triangles.
That's right. The word congruent you can introduce once you know, once children are slightly older and you want them to know that word congruent, and it's important that they should learn it in secondary school. Okay,
so they are exactly the same, and therefore you put the 2 together and they make a rectangle. But it's not something you know, it's something that when you play with it and investigate it, you think, oh well, and then if you play with it a lot, then you just really know it. And when you come to doing the geometry where we have to work these things out, you think, well, I know that a rectangle is made up of 2 right angle triangles. Just know it. There's no mystery to it. There's no at that point. Then you can make the next discoveries.
Well, what you can see here is that pink square, we made it, we told you earlier that the length of the edge of the square was exactly the same as the length of the longest edge of the blue triangles. And there you see them. That's the secret, that you can now fit those 5 pieces together to make a square, and it will fit into, those 5 pieces will split into a square frame.
And it's their same size. This is the beauty of taking the 2 and putting them inside the same frame. Is it doesn't necessarily look like it, but it so is. It's beautiful.
So you can then take the pink square out, and you can move the blue triangles into the position you see them for solution 2, and the spaces left are exactly right for you to put a green square and an orange square in to fill those places in the jigsaw.
Now, what if we called can I give them letters yet, Toni? Because this for me was a huge
no, we're not going to bother with that today. Okay,
it's just that the one thing that my mother remembered was a squared plus b squared equals c squared. That was one thing that she remembered, you know, in her 70s. She said, oh, a squared plus b squared equals c squared.
You're again a step ahead of everybody, Caroline.
I know, but that's why I say, can I say the letters? It's just that I'm seeing squares there. That's why I'm saying it. I want you to observe that you're seeing squares. Yeah.
Well, I wanted to make it totally free of algebra.
But I know, but it's squares. It's not algebra. It's the squares. The point is,
well, one thing that's
you've got 3 squares there, and I just want to notice that there's squares.
Yes. So what Caroline is saying is the edge length of the The green square you can call edge length A, and the orange square B, and the pink square C. And then let's just take it a step at a time, Caroline. What you have got
I'm
there.
too excited.
Now, you can place the 4 triangles in the position for solution 1. Now, that's without the pink square. What can you say about the space left uncovered? Okay.
So the space that's not covered by the squares. So the blue space, the space that's taken up by the triangle.
No, Caroline. No. What it is, Caroline, is read what it says, and I'll repeat it.
I did this before, didn't I? Here we go. Put the 4 triangles in the position. So the 4 triangles are in the box. So we have the 4 triangles. What do we have
uncovered
left?
In
what
the middle?
What is uncovered? So it's not the blue. It's the space that would be left.
So
there's no green, there's no yellow, and there's no pink.
But let's do solution 1. Okay. Let's go back to what this says. Put the 4 triangles in position for solution 1. Okay. And nothing else. Now, you can put the pink in and take it out again. So you can see that you can answer question 2. What's the area of that space in the middle between the 4 triangles? And you'll, as Caroline said, that if the edge length of the square is C, then the area of the square is C times C, which is C squared.
But the thing is that what I meant is when I said square is that you can name it a square. So C squared is something mysterious. When you say, oh, it's C squared, it can become something mysterious, which is why I was emphasizing the square. It is a square. It is just a square of edge length C, and it's just a square, and every edge is length C. So it's a square with length C, which just can be called not just can be called C squared, but the point is you can make the connection. It helps you make the connection between the expression C squared and a square where every length is C, and you can actually connect the two with a mental image of there's a square where every edge is length C and the expression C squared, and they're one and the same. And this is the beauty of this method. And it was very powerful.
What we were doing earlier was warming you up to be thinking about areas, okay, and counting squares inside and understanding what areas were about a little bit more. And so now to move on with this, now move the 4 triangles. You haven't got the pink square there. You're just going to move the 4 triangles into the position for solution 2. And that's, now you see them as 2 rectangles.
And they cover exactly the same space as they covered before. It's just that in a different shape.
Yeah, and they're in different positions in the frame.
They make a different shape because they make rectangles instead of being 4 individual triangles. They're still 4 individual triangles, but together they form 2 rectangles. Well, what do you have left? You have 2 squares.
Well, the big question is with just the 4 triangles in, but in the positions you see in solution 2, what's left? Well, the area for the green square, which is A times A area, and the area for the orange, which you see in that picture for orange square, if you put them in, and that's area B times B. And now the children will tell you, you're probably now with it, that the areas of the blue, whatever position they're in the frame, the blue triangles take up the same area. And what's left in solution 1, which is C squared, must be the same as what's left, that's the area of the pink, must be the same as what's left in solution 2, which is the sum of those 2 areas of the green and the orange squares as you see them there, A squared plus B squared. And so that gives you a result which is A squared plus b squared must be the same area as c squared. A squared plus b squared equals c squared. Or the area on the hypotenuse of a right angle triangle. Now look at the picture on the right, solution 2. The green triangle is up against the edge of the shortest edge, and the orange of the medium length edge. So those are the areas on the other two sides of the triangle. So the area on the hypotenuse is the sum of the areas on the other two sides. And when the children come up with that, without ever having met Pythagoras' theorem, you'll say, brilliant, you've discovered a big theorem in mathematics.
And this is, I could never, well, it took me a while to understand why Toni was talking about the young learners being mathematicians. And I've got it now. That whenever the young learners make a discovery, a mathematical discovery, doesn't matter if it's been made a million times before them, they have made the discovery. Therefore, they are thinking mathematically, they are being mathematicians.
Now, it's 6 o'clock, so we're going to have to wind up, but you see some links there, but I just realized there isn't the link, and I will put it in for the app, for the Geo Board app. But as Caroline said, just go to the App Store for Mac or the Play Store for Android devices, and you can find that app. But we'll give you the link. And so it's time to say goodbye.
Oh, sorry, I took that away. That was rude of me. Sorry. Goodbye.
Well, it's time. It's time to say.
Right, start again. Start again. It's
time to say goodbye. And what I was going to say was, we hope that it's what you've seen today is something that was fun from beginning to end. Maths lessons should be enjoyable, and it's also very powerful to teach in such a way as the children think that they're playing games, and yet they are learning, and they're likely to remember a lot more than if the teacher just tells them, these are the facts, this is what you must know, a squared plus b squared equals c squared, and now this is how you use it. And why should it make any sense?
That can come after. That's what I was talking about the squares, the green square and the blue square, whatever color they were, the yellow square, are the same as the pink square. And then when you talk about a squared and b squared and c squared, then it's like, well, yeah, it's those squares, and they can make the connections, and the visualization is, and they've got the experience to actually make sense when you start making it more formal, saying a squared plus b squared equals c squared.
Well, we hope that this has been interesting, and thank you now. If you're still with us, thank you very much for joining us today.
Well, we do have one viewer right this second. We've still got one viewer. Thank you very much for joining us. So I'm just going to say, I'm going to just give the last greeting for the recording. So thank you very much for joining us, and Toni, you say it as well.
Goodbye, everybody, and thank you for being with us.
See you next time.